Hi, welcome back. We're going to do some problem solving from the chapter of rotational motion, rotational dynamics and torques and so on. So there will be some calculus problems. There will be some problems that are easier than others. Um, so I'm going to do maybe 4 or 5 problems. Let's see where we get. Okay. So in this first problem here, it says, consider a cone of radius r and height h and mass capital M. The volume of a cone is 1/3 pi h r squared. They gave you that fact. What is the distance, or what is the distance from the apex to the center of mass, and then what is the moment of inertia, I, of the axis, about the axis of the cone? So let's look at the cone first. So this is the cone, and the cone looks like this. You can see it has circular cross sections. Those are circles. This is the apex, and they ask for the center of mass. You see, this is the heavier side because it's thicker, so we expect the center of mass to be somewhere here. It would be along the x-axis because it's symmetric about the y. It's symmetric about the x-axis. So the center of mass would have a coordinate y equal to 0, but the x-coordinate of the center of mass would be somewhere here. And we wish to find it. And remember that the center of mass, x center of mass, will equal to 1 over the total mass times the integral of x dm. Okay, x dm. So this cone has a mass capital M, and this is the volume of the cone. So it will have a density. I will call the density here rho. Density is mass over volume. So it would be capital M divided by 1/3 pi h r squared. So the 1/3 becomes a 3 because I'm dividing over it. And then I have pi h r to the second power. Okay? That will be the density. Now, how much is dm? How much is dm? Well, dm is how much mass is contained in so let's take a circular cross section of the cone of thickness dx. So here is the circular cross section of the cone. And it will have thickness dx. So this is the thickness of that section. So how much mass is contained here? Well, it will be the volume of this section times the density. So dm, let me calculate. So dm will be the density times the volume of this little cylinder, like a little coin, if you like, times the volume. So I'll call it dv, the volume of that. Now, what's the volume of a little cylinder here, a little coin? It's the area times the height. The area will be the height here, which is y. So that's the y. So the radius is y. So the area of this thing is pi r squared. So pi y squared times the thickness. The thickness is dx. And the location from here is x. The location of this is x. So that's the x part. So I get dm will equal to the density. And the density is this, 3 capital M divided by pi h r squared times dv. And again, the volume will be the cross-sectional area, which is pi y squared, pi times y squared. The height here is y. That is y. And the thickness is dx. But I have two variables, the y and the x, but they're related to each other. How is y related to x? Well, this is just a line, and the slope of the line is, this is the radius of the cone, and this is the height of the cone. And so the the y-intercept is 0 because it crosses this line crosses the y-axis, crosses the origin. So it's just y will equal to mx. It's usually mx plus b, right? The slope times x plus the y-intercept. The y-intercept is 0. So the slope would be the rise over the run. So when you get to here, the run is h, and the rise is r. So it's r divided by h. R divided by h. That's the slope. and this is x. So dm will be, let's clean this, so 3m divided by pi h r squared times, yeah, there is a, so no need to write this pi here, because this pi and this pi cancel. Now, what is y squared? Well, y is r over hx. So when you square them, you get r squared over h squared, you get r squared over h squared, and you square the x, you get x squared, and you get a dx. So the r squared cancels, and h times h is h cubed, so dm for this cone is 3m, 3 capital M, that's a constant. And h is constant, so h times h is h cubed, and times x squared dx. That's dm. Now we're ready to plug it here. So we get x, center of mass, will equal to 1 over capital M times x dm. And then x times dm. Well, dm is x squared dx, and then times all this stuff. And this stuff can be pulled out of the integral. So I get 3 capital M over h cubed. So 3 capital M over h cubed. So the m cancels. So here I have x cubed. Oh, where do we integrate? Well, we integrate whatever the mass is. The mass is found between x equal to 0 all the way to x equal to h. Oh, the coordinates of this point are h and r. H and r, right? The x coordinate is the height, and the y coordinate is the radius. Yeah. Okay. So you get x center of mass. Oh, we integrate from 0 to h. X center of mass will equal to 3 over h cubed, 3 over h cubed, times this integral. This is x times x squared, which is x cubed. The integral of x cubed is x to the 4th over 4. So 1/4 of x to the 4th, evaluated between 0 and h. So that's just h to the 4th power. And h to the 4th power divided by h cubed is just h. So you get h, and you have the 3/4 in front, and x center of mass. So that's the answer. The center of mass is somewhere here, 3/4 of h. This is h, so it's 3/4 of the way, which makes sense. It should be biased toward the heavy side in order for it to be the center of mass, to balance there. Sounds good? What's the next step? Well, the next, they want us to find the moment of inertia about an axis through the cone. So imagine you have a cone here and you want to spin the cone about that axis. So what is the moment of inertia of that? Well, the moment of inertia would be sum of many moments of inertia. So you have here a disk, this disk, and then another disk. So you take the moment of inertia of one disk and then add them. You stack them. You have, yeah, but the disks are of different radii, right? So remember the moment of inertia for a disk, let me call it di, because I'm choosing a disk here that's very thin. The moment of inertia for a disk would be 1/2 the mass of that disk. Because it's a small disk, I'm going to call it dm, because it will only contain a little mass. So 1/2 the mass of the disk times the radius squared of that disk. 1/2 mr squared. And instead of m, I have dm, and then r squared. And what's r? Well, the radius of the disk is y, which is r over h times x. R over h times x. And so I get 1/2. What's dm? Oh, nice. We found dm earlier. Here it is. It's 3 capital M over h cubed x squared dx. So let's write it down. So it is 3m over h cubed, and then x squared dx, this whole thing here is the dm part. And then here I have this thing squared. So I get r squared over h squared times x squared, like so. I think we have it. And so we need to just clean it a little. So di will equal to what? 1/2, so 3/2. And then I have mr squared, mr squared. And then x squared times x squared is x to the 4th. And then I have the dx. And then h cubed times h squared is h to the 5th power on the bottom. H to the 5th power on the bottom. And we just need to add up all of these moments of inertia, so we need to sum them up. So the total moment of inertia will be the sum of all of these moments of inertia. And so that is equal to 3/2 mr squared over h to the 5th x to the 4th dx integrated between, well, wherever the disks are found. The disks are found from x equal to 0 to x equal to h. Okay. And what's the integral of x to the 4th? It's x to the 5th over 5. But when you have a 1/5 and you multiply it by 3/2, so it becomes 3/10. Right? The 10 comes from the 1/5 you get by integrating and multiply it by 2 on the bottom. And then here I have mr squared, h to the 5th, and again here, when you integrate you get x to the 5th over 5, but the 5th we divided it here. And we evaluate between 0 and h. So when you put h to the 5th, cancels h to the 5th, and you just have 3/10 mr squared. Mr squared. That's the moment of inertia for a cone about its center. Let's go to the next question. This problem does not involve calculus. However, it's an important problem, and I think many books they don't discuss it in as much detail as I think they should. So we have a cylinder of radius r. This cylinder here is of radius r. The length of the cylinder is L. All we care about is a cylinder. So as far if it's a cylinder and it's rolling, we don't care. We only care about the radius. A cylinder rolling or a disc rolling, they're the same. Let me show you. What is this? A disc or a cylinder? Right? It's the same thing. A cylinder, usually it's a longer disc. It's kind of longer this way. It's a stack of discs together. So they have the same moment of inertia. It's 1/2 mr squared. The more discs you stack, the more mass you have. So it is 1/2 mr squared. So if you have 2 discs, it would be, the mass would be twice. But the moment of inertia is still 1/2 mr squared, where m is the total mass. So anyways, this is just the moment of inertia of it. And it's 1/2 mr squared. Now, it is released from rest, and it starts to spin, and then it falls. And then it says here, how much static friction is needed to prevent the cylinder from slipping? Because if we didn't have friction at all, the cylinder will just fall. It will never rotate this way. Because who is causing it to rotate about the center of mass? It's the force of static friction. Now, I drew the mass here, the mg. The gravity acts at the center of mass. When we did Newton's laws for point masses, it didn't matter where we just drew it downward. All it mattered was the magnitude and direction. Here, we actually care about where the force acts. It acts at the center. Next is the normal force. The normal force acts at the point of contact. Yeah, it is still that way, but it acts at the point of contact. This will be important in a moment. This is the normal force. And then there is the force of static friction. And in what direction is it? The books will tell you that it's this way. And it is. And the argument, let me put it this way. The argument they give is that if it's accelerating this way, if it's the angular velocity is increasing, somebody has to be applying a torque, and it has to be the force of static friction, and it's this way, whether you're going up or you're going down. Because if you're going up, you will be slowing down, so you need the force of torque this way. I don't really like that argument. I know there is force of static friction. Actually, let me take it back. That argument is fine, but I don't think it's rigorous enough. So I want to show you, prove to you definitively that the force of static friction has to be up the incline, not down. Whether you're rolling up the incline or rolling down the incline, the force of static friction, if you're rolling without slipping, it has to be up the incline. I want to show you why that is the case. Okay? Let me go to the next table. I'm going to redraw this on the whiteboard here, and then come back to this problem. So here is this is theta here. This is mg. This is the normal force. And the force of static friction is in a certain direction. I know it's friction, so it acts along. So we can assume that the force of static friction maybe is this way, is up the incline. If it's up the incline, then we'll just get a magnitude that's positive. If it's actually different than what we have assumed, then we'll get a negative value, okay? So how are we going to calculate it? Well, first of all, the gravity will have two components. One of them is this way, mg sine theta, and one of them is this way, mg cosine theta. First, there is no acceleration in the y direction, therefore the normal force will equal to mg times the cosine theta. Next, I want to calculate the angular acceleration of the disk as it falls. Now, to calculate the angular acceleration, I have to find the torque and then set it equal to I alpha. The problem is I don't know how much is the static frictional force, so that's an n-noun. So if I want the torque due to the static friction force, I need to know the force of static friction. To avoid that, remember, we can choose our axis of rotation here at the point of contact, because remember we said if the disk is this point here, it's at rest. We proved that. We showed that it is at rest. And it's as if this is the instantaneous axis of rotation. So I'm going to calculate the torque about this point. And the torque about this point will equal to the moment of inertia about this point times the angular acceleration, and see what we get. All right, so let's see. So I get the torque about that point, will equal to the moment of inertia about that point times the angular acceleration. The torque, now, the torque will consist of three torques. There is the torque due to the force of static friction, plus the torque due to the normal force, plus the torque due to the mg. All right? And that equals to the moment of inertia times the angular acceleration. The moment of inertia about this point will equal to the moment of inertia about the center of mass plus the mass times the radius squared. Where does this come from? Well, the parallel axis theorem, right? So if you know the moment of inertia about the center, you can calculate the moment of inertia about any point through which an axis passes parallel to the axis of the center of mass. And then here I have alpha. So the torque due to the force of static friction, remember, to calculate torque you need r times f times the sine of theta. How far is the force of friction from here? Well, the force of static friction acts at that point, so it contributes 0 to the torque. The same thing for the normal force. The normal force acts at that point, so it contributes 0 to the torque. And it's also this way. So these two contribute nothing to the torque. The mg contributes something. Remember, to calculate the torque about a point, you need the arm length and then the force that's perpendicular to that arm length. And the force perpendicular to here, well, it's the mg, but only this part of the mg contributes to the torque. So it's the mg times r. So it would be mg, only the perpendicular component. So mg sine theta times r, and that equals to the moment of inertia about the center of mass times mr squared. But what is the moment of inertia about the center of mass? The moment of inertia about the center of mass is always some constant times mr squared, some positive, some non-negative constant, right? C here, if it's a disk, it will be 1/2 mr squared, so C would be 1/2. If it's a sphere, a solid sphere, then it would be 2/5 mr squared, so C would be 2/5. If it's a hoop, it's mr squared, so in that case C is equal to 1, so on and so forth. So C is some just constant that's not negative, it's a non-negative constant. So for the moment of inertia, I'll write C about the center of mass, so it's C times mr squared plus mr squared times alpha. And so I will get r mg sine theta will equal to C plus 1 times mr squared, I factored the mr squared, alpha. And so the mass cancels, one of the r's here cancels, and so I get g sine theta will equal to C plus 1 times r times alpha. If we're rolling without slipping, it implies that the linear acceleration would equal to alpha times r, or r alpha. So this part is the linear acceleration. So therefore I get g sine theta will equal to 1 plus c times the linear acceleration. And therefore the linear acceleration will equal to g sine theta divided by 1 plus this constant c. Remember, c is some non-negative constant, so it will be 1 plus 1/2, or 1 plus 1, or 1 plus 2/5, or 1 plus 3/5. So this number here would be larger than 1, so the acceleration would be less than g sine theta. It would be less than g sine theta. So let me just box this. We will need it in a moment. Now, we look at the sum of the torques. Now let's look at the net force in this direction. Let's call it the x direction. So what is the net force there? Because I want to... The net force there, it will be... I know that mg sine theta is in the positive x direction, so I have mg sine theta. I'm going to assume that the force of friction is up, so it's minus Fs, and it's parallel. Now you might say, why didn't I assume it's down? You could assume it's down, and then you will, you just have to assume it's somewhere, either up or down, and then if you assume it's up and you get a positive value for it, then you're fine. If you assume it's up and then you get a negative value for it, it means it's opposite to the assumption, to your assumption. Here, I'm guessing it's up because it's increasing, so I know that somebody is pushing the disk this way to cause it to spin faster and faster. So it's a good guess, and it will not turn out to be the correct answer. You might say, well, since we guessed it and it's right, why did we have to go through all this math and physics? The reason is I want to show you definitively that this is the case, not just wave my hands and hope that you understand it. So we have this. This is the net force in the x direction. It will equal to the mass times the acceleration in the x direction. So let's solve for Fs. Move Fs here and this one here. So you get the force of static friction will equal to mg sine theta. Move this here, so you get minus ma, like so, right? Move this here, so you get mg sine theta minus ma. Move the force of static friction here, so it becomes positive. So let's see. So if mg sine theta minus ma turns out to be positive, then my assumption is correct. If mg sine theta minus ma turns out to be a negative number, it means the friction is actually in the opposite direction to what I have assumed. Let's see what we get. So I get Fs, the force of static friction, equals to mg sine theta minus ma. But the acceleration is g sine theta over 1 plus c. So I get m times the acceleration, which is g sine theta over 1 plus c. Now, is this larger than 0 or not? The answer is yes, it is. Because you have mg sine theta minus mg sine theta divided by a number that's larger than 1. So this ends up being less than, this part is greater than this part. So this is greater or equal to 0. And therefore, it's only 0 when c is equal to 0 for point masses. That means friction is up the incline. So now we have proven it, all right? It is up the incline, definitively. Now, how much is the friction if you have a disk? What is the force of static friction if you have a disk? Well, for a disk, remember the moment of inertia about the center of mass. For a disk or a cylinder, it is 1/2 mr squared, which is, we said c mr squared. So c will equal to the 1/2 for a disk. So let's calculate the force of friction for a disk. So the force of static friction, if we have a disk rolling or a cylinder, as in this problem we had, I'm going to roll the board down, but let me just write down what the friction should be. So it would be mg sine theta minus mg sine theta divided by 1 plus c. 1 plus c is 1/2. Right? Is 1/2. 1/2 plus 1 is 3/2, but you're dividing by 3/2, so it becomes 2/3. So you have mg sine theta minus 2/3 mg sine theta. 1 minus 2/3 is 1/3, and therefore the force of static friction will equal to 1/3 mg sine theta. This is for a disk. Right? Don't say it's always mg sine theta. It's only mg sine theta for a disk, because for a disk, c here was 1/2. If you had a sphere, it would be 2/5, and so you'd have here plus 2/5, and it would be something else, 2/5. It was like 2/7 or 7/5, something like that. I forget what so it would be something else if it were a solid sphere. So that's that. Let's go back to our board here. They said, what is the force of static friction needed to prevent slipping? Well, let me write down the force of static friction. I figured that the magnitude of the force of static friction better be 1/3 of mg sine theta. Now, the force of static friction, the maximum, let's say you have reached the maximum here and you don't want to slip. It is related to the normal force by μs times the normal force, And the normal force is normal force this way, mg cosine theta, this way. So the normal force is mg cosine theta. So it's mg the cosine of theta, and I have μs here. So these two are equal. So let's see what we get. So you get 1/3 mg sine theta will equal to μs mg cosine theta. The mg's cancel. Divide by cosine and you get tangent, and so you get μs will be 1/3 of the tangent of theta. So if μs is, if you chose an angle, and μs happens to be 1/3 of that angle, then you will not slip. You're about to slip. If you increase the angle a little bit, then us will be less than the 1/3 of tangent of that angle, and so you have reached the maximum friction, but you can't keep up with this, and so it will start to slip. So that is the answer. Oh, 30 minutes already. Good timing. 2 problems in 30 minutes. So I will stop this and I will see you in the next video.